Okay, so here is your free response question for today. Just organize here. All right, so for this free response question, you're given a table of values. One thing I'm aware of right away is that the y value, or the output, is a rate. So right away I noticed that's going to be important to me, that represents a rate. So water is being pumped into a tank, rate modeled by W at T equals that. Now this table of values is not W, so this is separate from the table of values. From 0 to 8, where 8, that's in hours, where T is measured in hours, water is removed from the tank, modeled by this, R at T. So what I'm looking for here is what's being removed at what rate, and we're given another equation about the rate that water is being pumped in. Selected values of it are given and are shown in the table above. At time t, there are 50,000 liters. And notice that R is differentiable and decreasing. Differentiable means it's continuous all the way through, and that's going to be important. Okay, let's start with A and how we would answer it. So in part A, it says, can you estimate the derivative of R at 2 and show the works that leads to your answer and the units of measure you would use. So if I was going to estimate the derivative at 2, notice 2 is not given in this table. So the estimate would be the slope around. So slope is derivative, and the slope that surrounds 2 would be the estimate for that. So all I have to do is find the slope there. So a good estimate for that, and I don't need to simplify it, would be simply finding slope. So that's 950 subtract 1190, and then 3 subtract 1. That should be in the numerator. So 1190 subtract 950 is in the numerator. 3 subtract 1 is in the denominator. And there's no need to simplify that, but if you did, you get negative 120. But now the units, which are important. So what units was it? It was liters per hour. So what would the derivative of a derivative be? And it's liters per hour, or liters per hour squared. And part A is done. Part B. Use a left Riemann sum with 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. Is this an over or underestimate? And so, and give a reason for your answer. Let's first start with the left Riemann sum with this. So the first thing I look at are the x or t values. Are those equal intervals? No. 0 to 1, 1 to 3, 3 to 6, 6 to 8. So that means that I have to handle each rectangle separately, the area of them, and I can't just put down the width in front, parentheses, and add up the height. So I have to handle each rectangle separately. So the first rectangle, how wide is it? It's 1. And then a left Riemann sum, which number would you use? And it would be the left value for the height, which is 1,340. So I'm just going to follow that pattern. So first of all, I'm going to write down what I'm doing. I'm integrating from 0 to 8. R at t dt, that's what I'm doing. I'm estimating, so it's approximate sign. So I start with the first width is 1, and then I'm using 1340. The next width is 2. Notice 3 take away 1. And then again, left Riemann sum, 1190. Next, 3 to 6 is 3. And the left Riemann sum is using 950. And then the last one's from 6 to 8. Well, that width is 2. And again, a left Riemann sum, you'd use 740. So always using the left values for the height of the rectangle. I don't have to simplify that. If I did simplify it, it would be 8,050. Now, the units, what would happen if you're integrating a rate? So if you're integrating a rate, it's no longer a rate. Instead, it's the unit. So what has accumulated is how many liters have been removed. And so the answer is from t equals 0 to t equals 8 hours, 8,050 liters have been removed from the tank. And then the second part is, is that answer an underestimate or overestimate of what it actually is? So two things I'm looking at. So first I'm looking at to know if it's an over or underestimate is if it's increasing or decreasing. And I might even just give myself a visual. This is decreasing. So there's my decreasing, just a quick visual. And I'm using a left Riemann sum. So when you do a left Riemann sum, is that going to be an over? And as soon as you get a picture of it, if you forget, decreasing with a left Riemann sum, you can see the rectangles are going over the curve. Like there is more area above than what it actually is. This is an overestimate. So you would say it is an overestimate. Why? What two words would we use then? Overestimate. I can spell that word. Because R at T is decreasing with a left Riemann sum. I'm just going to write right over these words. So the two words they'd be looking for the reason why it's an overestimate is that it's decreasing with a left Riemann sum. All right, I'm going to go to another piece of paper here. So part C. So I'll just label it real quick. This is 2018 free response question number 2016. I'm sorry, 2016, and it's a free response question number 1. Let's look at it. So 1C. So in 1C it says use your answer from part B and to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. So our goal is to find out how much water would be in the tank. So first of all, in the question, does it tell me how much water we're starting with? So if you read at the very end of the prompt, how much water do we start with? 50,000. So we're going to start with 50,000. Then we're going to subtract what we just came up with. So how much water is being removed? And it was 8,050. That's what we just came up with in B. Then we have to add the water being pumped in. Now, is there a model to use that? And this one, again, we're going to integrate from 0 to 8. But we're going to need our calculator now to finish it off. So that's the equation of how much water is being pumped in. So let's type that in together with our calculator. Let me just clear this quick. All right, so to type this in, 50,000, subtract that estimate, 8,050, and then we're going to add, now we're going to integrate. So we're going to press to be able to integrate this. And we're integrating from 0 to 8. And then I have to type in the equation, which is 2,000 E. And then it's negative, I don't mind using t, so I can go negative t squared. So it's negative t squared divided by 20. That's all in the exponent, and that's dt. And then control enter. And so approximately how many liters are in there? And it says to the nearest liter. So in the question it says don't go 3, it says just to the nearest liter. So that's 786. And that's left in the tank after 8 hours. All right, one more. 1D. One D says, from 0 to 8, is there a time t when the rate at which the water is being pumped into the tank, so what's being pumped into the tank is W at t, is there a time in which that is equal to the rate being pumped out of the tank? So is there a t value for that? Is there some time when that would happen? And how could I prove it? I don't know when that would be exactly, but explain, is there a time such as? So this is a theorem question. And to understand it, first of all, I'm going to first look at the initial rate. So at 0, what is the initial rate? So I don't need a calculator for this. So when I plug in 0, e to the 0 is 1, so it's just 2,000. So initially there's 2,000 liters per hour being pumped in and then out at the same time. So look at the table. You can see it's 1,340. So right now, at first, we know that the rate of the water going in is bigger than the rate of the water going out. What we need to do is find a rate, an hour, where it's been flipped, where the one rate is smaller than the other. So right now, the water going in is bigger than the water going out. Is there a time the other way? So if I go at the very end, so if I look at 8, an hour 8, the answer here is 700 liters per hour. If I look at 8 in our equation and just plug it in, what answer does that give me? So that is 2,000 E, and it's to the negative 8 squared divided by 20. And I get 81. So negative 8 squared divided by 20, 2,000. I get 81 point something. So what did you notice? That now, during the 8th hour, the rates have switched. So now the rate of the water leaving is bigger than the rate of the water going in. So because of this, there must be a time between t equals 0 and t equals 8 hours where W at t equals R at t because of the intermediate value theorem. Since both functions are continuous. So the intermediate value theorem, if one starts out greater than the other and it switches and they're both continuous, if you would graph them both at the same time, they have to intersect at least at one point where they would be equal to each other. So you have one graph where it's going like this and another graph maybe going like this. There has to be a time, if they flipped, where they intersect. So if there's a time where one is greater and then it flips where the other one is greater and they're continuous, there must be a time in that interval where they're equal to each other. And that is called the intermediate value theorem. And you're done. So, great job doing your work. Mr. G Math, over and out. I'm proud of you. And until next time, we'll keep practicing. All right.